This is the 311 notes for Calculus 1. One of the biggest applications of derivatives has to do with the concept that the derivative of a function represents the rate of change of our function f. So as an example, if you recall, we had our flow chart where it was position, take the derivative, get velocity, take the derivative, get acceleration. So basically, this is s prime. So if you take the derivative of position, you get velocity. So we would say that the velocity is the rate of change of position. So that should make sense to you. You know, as you're changing positions, the rate in which you're doing so is the velocity in which you're traveling. Similar, we know that acceleration is v prime. So we would say that acceleration is the rate of change of velocity. So the key concept, though, again, here is all about rate of change, because that is what the section is about. It's called related rates. Now, what's the word related come from? It comes from the fact that we're going to have two or more variables changing at a time with respect to time. So right now, we're just talking about a single variable here. So basically, in this scenario, we're going to have multiple variables that are going to be changing with respect to time, and that's where we're going to be going with this. Okay, let's look at an example. It says an oil rig springs a leak into calm seas, and the oil spreads in a circular patch around the rig. Okay, so in the picture here, we have a rig here, and it appears that it is spreading outwardly in a circle. Now, obviously, this is not something that would actually happen, but it's great for an example problem. What is it we're looking for? It says, if the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? Well, clearly, what you're looking at here is a very typical word problem, and that will be the case in every problem in this section. It's all about, they'll be giving you regular measurements and rates, and you'll have to find usually rates in the problem. In this case, it is a rate. It says, how fast is the area of the patch increasing? That is a rate. So what we want to do is, let's break it down into pieces and see if we can figure out how to do this problem the way you should do it in a related rate scenario. Okay, the first goal in a related rates problem is to identify the two or more variables that are changing simultaneously. Okay, so what two variables are changing in this problem? Well, clearly, as the oil spreads, what's happening to the radius? It's becoming larger. So we know that one of the variables we'll call r is the radius. Okay, that will be one of the variables that is changing. But we also know that as the radius changes, what else is changing? Well, what is another concept in this problem that was provided? It looks like the area is changing. So we're going to use big A for area. So that's what makes this a related rates problem right here. Because we have two or more variables that are changing with respect to time. So if you look at this, what's happening? Over time, the area and the radius is changing. So what do we need to do next? It says we now need to find a key relationship between the two variables, area and radius, when it comes to the circle. This usually comes in the form of an equation or a formula. Okay, so hopefully when you think of area and radius of a circle, you immediately think of the area formula for a circle, which is area equals pi r squared. Okay, so now this is where we end up getting into the calculus, which is going to be a little bit funky for the brain, but stick with me here. It says once we have some type of equation or formula, which we do, we need to find the rate of change. In this case, we need to find the rate of change of area with respect to time. Okay, real quick. Going back to our problem itself, what did they ask for? It says, how fast is the area of the patch increasing? So what is that? That is the rate of change of area with respect to time. Rate of change of area with respect to time. Okay, so that is what we're trying to find. So how would we represent that in terms of a variable? We would say that that is dA dt. Why would we say that? Well, normally, what do we have? We have dy dx, right? So this is the derivative of y with respect to x. It's also the rate of change of y with respect to x. So what are we doing? All we're doing is we're changing the variables so that we're saying rate of change of area with respect to time. So that is dA dt. So what is that? Well, that is the area formulas, basically the derivative of the area, right? So note, we're taking, in order to produce this variable, we need to take d dt of both sides of the equations. So what is this going to be like? This is going to be like implicit differentiation in a nutshell. So this is why one of the reasons you learn about implicit differentiation is to do related rates. So what does this entail? So once you look at this formula, we should be able to work this out and find the derivative. Now note, it's not d dx because we don't have a variable x. In every single problem we do in this section, it's going to be d dt, so at least you have that to fall back on in terms of memorization. Okay, so this is where it gets a little tricky, all right? So what we need to do is we need to convert this. So normally, when we find d dx of y, what is that the same as? Well, what did we do? We took the y up here and we got dy dx, right? So this right here is going to end up being dA dt, which is exactly the variable that we're trying to find in our problem right here. Okay, what about the right side? This is a little tricky. So note that pi is a constant, so that is essentially just along for the ride. So that means we can technically move the pi outside the derivative symbol, and we are going to take d dt of r squared. Okay, d dt of r squared. Now, what happened when we took, let's go over here, when we took d dx of y squared? What happened? We decided, oh, the variables don't match, right? So what did we do? We said, all right, take the derivative as if it was x, but then have a y in there, so 2y, and then multiply by dy dx. So what is this going to become here? Well, we take the derivative as if it was a t and but have an r in it, so 2r, and then multiply by dr dt. So I know this is tricky for sure in the beginning, but all you have to do is change your implicit differentiation work into different variables, and you're doing the same thing. So what's the formula? You get dA dt is equal to, you have pi and 2r, so we'll do 2 pi r times dr dt. Okay, so this right here is our implicit differentiation formula that we're going to need to do the rest of the problem. Okay, so now that we have the rate of change of area with respect to time, right here, rate of change of area with respect to time, we can bring the given information into the problem. The original problem gave us the radius of the patch of oil, which is 100 meters, right? So note the radius is right here, just r, as well as the rate of change of radius. So remember, it gave us the radius is 100, but it also gave you the rate of how the radius increases, which is 30 meters per hour. So what is the rate of change of radius variable in our problem? Well, if this is the rate of change of area, then this is the rate of change of radius. So this is that variable dr dt. So it says simply substitute all the given information into the derivative we developed earlier and solve for the rate of change of area. Okay, so let's do that. So we have dA dt, which we're trying to find. 2 pi is a constant. We have r, which was given to us as 100 meters. And we have dr dt, which is the rate of change of radius, which was given to us as 30 meters per hour. Okay, therefore, we should be able to solve this. I'm actually not going to put it there. We can be able to solve this by just multiplying it out. So we can do it in terms of pi. So we could do 2 times 100 is 200 times 30 is 6,000 times pi. So we get 6,000 pi as our result. If you want to multiply that out, you can. I think you're going to get, if you do 6,000 pi, you're going to get about 18,849 around there. But the key is with related rates is you need a label. Okay, you need a label, and that's going to be sort of a big thing here. So what is an I'm actually going to put it back over here so that I can show you something. So what's one way to determine the area? Well, we know that the 100 radius of 100 was in meters, and we know that the rate of change of the radius was in meters per hour right here. So note, just like we do with the numbers, we can also multiply the labels and get m times m over hr, which is m squared over hr. So the label is going to be meters squared per hour for our result. So how do we know that? Well, it's actually kind of easy, because all area will create a squared label. So like if I have the area in meters, it's going to be meters squared. But if it's a rate, then it has to be per time, so it's going to be meters squared per hour. You can do it, eventually you're going to get used to it and you're going to come up with the labels fast, but till then you can always use the actual labels of the individual ones, multiply them and get the result. So the rate area of this patch of oil is increasing at 6,000 pi meters squared per hour since the original, at the time of this going on with our specific problem. Okay, that was a good intro to what you need to do, but obviously you're going to need some practice here. So I'm going to go through some problems with you to make sure all is good in understanding it. Note that most of these related rate problems specifically deal with area and volume formulas. Not always, but a lot of them do. So be prepared to search around the internet for formulas that you don't know if you're doing homeworks and such. Usually on exams I provide those formulas, but if it's an online class, I'm not sure how that's going to work. I'm not there yet, but just be aware of that. So number 1, it says, suppose that we have a square that is increasing in size. Specifically, the lengths are increasing at a rate of 5 meters per second. At what rate is the area of the square changing when the sides are 50 meters long? So usually what I do is I first draw the picture. So basically we have a square. Okay, that's the first thing. Square. I also usually try to identify what we're trying to find. It says, at what rate is the area of the square changing? So again, what are they looking for? They're looking for the rate of change of area. So we know that that is going to be, from our previous problem, dA dt. Okay, we know that that's the case. And by the way, if it was volume, what would it be? It would be dV dt, because it's the rate of change of whatever the measure is with respect to time. So what we need to do is we need to come up with variables for the other things. So it says the sides have a length of 50 meters. So note that that is not a rate. That is just a strict side length, which means that is a simple variable. We'll call the sides x, which means up here it says the lengths are increasing at a rate of 5 meters per second. So that's the change in sides with respect to time. So that should be dx dt in our problem. So in the beginning, I have a feeling students will struggle with labeling that. You might need to figure that out later. I don't know, but that's going to be the idea. So if we have a square, we know now that the side length is x, which means, by the way, all of them are going to be x, technically, if you want to be specific. So what we need to do is we need to find a way to relate what we're trying to find, which is area, to the sides of our square. Well, clearly, we can find that the area is equal to what in a square? If the side is x, it's equal to x squared. So our formula for our problem is going to be area equals x squared. Now, what do we need to do with that formula? We need to find the derivative with respect to time of each side. Okay, why do we need to do that? Because by doing so, we are going to develop both of our rate variables. That is the key. That's why we do it. We need to form those rate variables, and you can't do that without taking the derivative with respect to time of both sides. So as we did before, so this is going to be the derivative of a with respect to t, dA dt. Over here, what do we have? We have two variables that don't match. And by the way, are they ever going to match? No. So feel free to just assume everything's implicit. So in order to do that, how does that work? Well, we take the derivative of this as if it was a t. So if it was t squared, it would be 2t. So now it'll be 2x. And then we multiply by the derivative of with respect to this variable, x, always till time. So look at what we just did by just doing implicit differentiation in this step here. We created our three variables in our new problem. So this is our related rates equation. We can now substitute in all the important numbers and find what we need. So again, what we're trying to find? We're trying to find this right here, right? So dA dt is the missing variable. What do we plug in for x? Well, the length of the sides is just 50. And dx dt right over here is the rate of change of the sides, which is given at, it says increasing at 5 meters per second. Okay, so I'm going to put the labels below it. So this is in meters, and this is meters per second. So if we do the math, we're going to get 2 times 50 times 5, which is 500. If we multiply this out, we're going to get meters squared per second, which means that is the rate of change of area for our square as it's increasing. Okay, so number 2. It says the area of an isosceles right triangle is decreasing at a rate of 15 square meters per second. So interestingly enough, this is the first time we've seen the word decreasing. In all the other problems, it was increasing, so that's changed some stuff. It says, at what rate are the legs of the triangle changing at the exact time when they are 5 meters long? Interesting. All right, so the first thing we want to do is we want to draw an isosceles right triangle. Well, an isosceles right triangle you can draw in a couple different ways, but clearly isosceles means that there is a right angle, or there's a isosceles means there's two sides that are the same, and there's a right angle between them, essentially, right? Now, the thing is about that is the way that is drawn can be a little bit tough, because what are we trying to find in this problem? Or what are we given in this problem? We're actually given the area and the rate in which it's changing. So what we're going to have to do is we're going to have to label each side with a variable. So these two will be x, right? Just note, remember we used tick marks back then in geometry to represent two sides that are the same. But if I need to find the area of this, is everybody going to understand exactly what to do there? Sometimes students need to draw the figure sideways to understand that we're doing basically half base times height. So the area formula for a triangle is half base times height. But in our setting, that's half x times x, which is going to be 1/2 x squared. So the area of that we're going to be working with is this, basically, 1/2 x squared. Okay, this is something you have to be able to develop on your own. It's just middle school geometry kind of thing that you'll be working with. So once you have this formula, we have to come up with the related rates formula. So as we've been doing before, we have to take ddt of both sides. So ddt of a, ddt of 1/2 x squared. Okay, So where do we go with that? Well, right away, we know this becomes d/t, but remember that this half right here is a constant. So that's basically not going to be treated as anything of relevance other than moving it to the front. So you're going to get 1/2 d/dt of x squared, like that, and then you can go ahead and find your result. So the 1/2 stays put. We have two variables that don't match, so we're going to do the derivative of x squared as if it was a t. We would get 2x, but then we would have to multiply by dx dt. So this, we just have to simplify and get d/dt is equal to 1/2 of 2 is 1, so we're just going to get literally x dx dt. Okay, so this is our formula for our problem. Now, let's look at what was given and see if we can do a little work to figure out what needs to be plugged in and where. So it says the area of an isosceles right triangle is decreasing at a rate of 15 square meters per second. Okay, so which variable is that? That is the key. Hopefully everybody clearly sees that it's the rate of change of area, which is the left side of the equation. So this time, we're not trying to find this, we're actually given this. So in our problem, that is 15 square meters per second, but look at this word here. It's not positive, it's negative 15, which is going to be the left side of the equation. So note that that is in meters squared per second. Okay? So on the right side, what else do they give you? They say at what rate are the legs of the triangle changing when they are 5 meters long. So they're telling you that the legs are exactly 5 in meters. And what are they trying to find? It says at what rate are the legs of the triangle changing? Well, what variable represents the legs? X. So if it's changing, it's dx dt, which is going to be our missing variable. Okay, so what do? We solve for dx dt on our right side by dividing both sides by 5, and we're going to get -3 as a result. But what's the label? All right, well, we could do it mathematically. So as we divide 5 this way, we're dividing meters squared per second over basically m. When we divide by m, it's the same as multiplying by 1 over m. If we cancel these out, we get m over s, which is going to be our label. But you should kind of know that already, because all of these problems, that was what was given. Anytime you had a single measure, like a single leg or side or anything, a radius, they're all in a single unit of measurement. So it should be a single m per second. Whereas if it's area, it's m squared per second. If it's volume, it's m cubed per second. That should be pretty simple to remember. So basically, this is our answer to our problem. Now, I need to do an aside here. Okay, there's a little bit of wordplay that you have to be careful of. So note, I said at what rate are the legs of the triangle changing? Because I said that, it didn't take into account positivity or negativity, so I have to include it in the answer. Now, what if I asked, at what rate are the legs of the triangle decreasing? Then the answer would have been just 3 meters per second. Hopefully everybody understands that when they're sort of following this, is that it's sort of changing means you have to designate, if it's increasing or decreasing. But if it says decreasing already, then you should be just writing 3 meters per second, because if you write a negative, it's like a double negative. Not only it's negative, but it said it was decreasing. So hypothetically, I guess it would go positive. I don't even want to go there. But the reason why I'm saying this to you is not because I care that much about labs and exams, but in my math lab, they get very picky about that. So make sure you pay attention to the wording of problems. Before we move on to 3 and 4, I just want to note, I am aware how incredibly confusing this probably is right here. Because in the previous implicit differentiation section, say that 40 times fast. If we took the derivative with respect to x of x squared, those are the ones that were easy, right? That was just 2x and we're done. So now all of a sudden the x's become something you have to handle implicitly because the variable here changes to t. So now all of a sudden this has to become 2x dx dt. So I know that's incredibly confusing, but the key is it's got to be, you have to understand what variable you're taking the derivative with respect to and how that's going to alter whatever the variable is that you're finding. So just a note of that, just in case that's hurting your head right now. It's all about the variable you're taking with respect to versus the variable you're actually taking of in the parentheses. Okay, so let's move on to 3 dimensions. It says, number 3, the side of a cube decreases at a rate of 2 feet per minute. What is the rate of change of volume when the side lengths are 12 feet? Okay, so now we're in cube world. So if we have a cube, how do we do that? We do a square, approximate, and then we just make it in 3 dimensions, something like that. If you want to be artsy-fartsy about it, you can do that. So let's again, maybe we'll change it up a little bit. So maybe we'll make S be the side of a cube, just do something different, which means that all of these dimensions are S all the way around, correct? And we're looking in volume, so we need a volume formula. So remember, volume is length times width times height, which are all S's in this problem, which means if we do that, we get S cubed, so volume equals S cubed will be our formula. So maybe this will pay off doing this, so just a good example, using a different variable than X. So what do we got? We have to take ddt of both sides, so ddt of capital V, ddt of S cubed. All right, so this is going to be dv dt. There's no constant, it's on the right, so we can look at this and go, all right, different variables. So what does that contain? So we have to find this derivative as if it was just a t. So it's going to be 3s squared, but then we have to multiply by the change in that variable s with respect to t. So hopefully you understand we did dx dt up here, and we have to change it to ds dt because of the variable change. Worth doing just in case students didn't understand before. Okay, so what does that look like? Well, we have to, actually, let's not put it there. Let's put it below. So we have to find what we're given. So what's the first thing we're given? We're given the side of the cube decreases at 2 feet per minute. Okay, so it's a rate and the size. So what's the rate of side change? It's right here. So that's going to be -2 in the scope of our problem. So it's decreasing at a rate of 2 feet per minute. Let's put feet per minute underneath that. I usually do it in a different color. That's probably a good idea to do. Feet per minute. All right, so what's next? It says, what is the rate of change of volume? Okay, so that means that dv dt is what we're trying to find, so we leave it put as is. We have a constant 3, and then we have the variable s squared. Well, what's the variable s? S is just a simple length of a side, which is 12 feet. Okay, so this is in right here. This 12 is in feet. So if we do the multiplication, we're going to get 3 times 12 squared times -2, which is -864, and then we need a label. Okay, note, it's not feet squared per minute. Why? Because this feet, which is the 12 feet, is being squared to get feet squared, then multiplied by feet to get feet cubed over minutes, which means the answer to the problem is -864 feet cubed per minute in terms of how the volume of this cube is changing if the sides are decreasing. Okay, so let's move away from sharp edges here, straight edges, and move towards a more circular object. This is air is being pumped into a spherical balloon at a rate of 20 cubic inches per minute. How fast is the radius of the balloon increasing when the radius is 6 inches? Okay, most balloons aren't perfect spheres, but again, for the purposes of our problem, we're going to assume that. So how can we draw a sphere? We can just draw a circle and then do sort of a in-between thing here. So that'll be our sphere, not the most artistic sphere, but good enough. When we have a sphere, of course, we have a radius. So we'll just put that there as r for the scope of our problem. All right, so the one thing we need is we need to find out what's going on in this problem. So what are the things that are changing? The radius is changing, which we need to find. And then what is happening with the air? What's increasing within the problem? Well, hopefully the thing that gives it away is cubic inches per minute. So that's a rate of change of a volume. So that means that variables at play here are v and t, or v and r, with respect to t. So we need the formula for the volume of a sphere. A lot of students, most students don't know that off the top of their head, but funny enough, every semester in class that I actually ask students, I always have one person that knows, which is pretty cool. It's 4/3 pi r cubed. All right, so we need to take the derivative with respect to t of both sides of this. Note that we have a constant of 4/3 pi. We might as well get smart about that and move it out just in the beginning of the problem. We've been writing out a lot of steps, so why not get smart about it, move it. So we're going to get dv dt over here. 4/3 pi comes along for the ride. The derivative with respect to t of r cubed means that we have to find the derivative of r cubed as if it was a t, but then multiply by the derivative of that variable r with respect to time. All right, the only thing left is we want to simplify. If we look at our problem here, we have 3's that cancel, so we're going to end up with 4 pi r squared times dr dt. All right, so the only thing left is to go back into our problem and find out what we were given. So we have air being pumped in at a rate of 20 cubic inches per minute. So that means that that is the volume change of rate, which is over here. It's being pumped in, so it's increasing, and that's at inches cubed per minute. Okay. On the right side, we have our constant 4 pi, and then it says the radius. Well, if you look, we were given the radius of 6 inches, so that means that's 6 squared. Now note that the label for that is going to be in inches, but we don't want to lose track of the squared. It's going to be ultimately inches squared in the long run. And look at what we're trying to find, how fast the radius is increasing of the balloon. Well, that is the rate of change of radius right here, so that's our missing variable. Okay, if we do the math, it looks like it's going to be 20 is equal to 144 pi dr dt, which means when we divide, we're going to get dr dt is equal to 20 divided by 144 pi. And then if it's inches squared divided into inches cubed per minute, it's just going to be inches per minute. Inches per minute as our label. So that is going to be the rate of change of radius. If you wanted to do the decimal for that, and in some problems you might have to, I think it's approximately 0.00442, but that is your rate of change of radius for our spherical balloon. Okay, the good news is usually by this point, most students are getting it. You know, even though it was a little bit of abrupt change in the beginning, most students see that it's just a variation of implicit differentiation as a way to find these rates in a problem. The bad news is you've by far done the easier problems. Usually in related rates problems, there's like A, B, and C level problems. You've done the A problems. We're going to do the B level problems now, and I don't really cover the C level problems. I don't think we need to go there in a summer course. You have enough on your plate. But basically, that's where we're going now. We're starting the B level problems. Number 5. It says a 20-foot long ladder is leaning against the wall. The bottom of the ladder is sliding away from the wall at a rate of 2.5 feet per second. At the exact time, it is 12 feet from the wall. Okay, so in our picture, we basically have, this is a ladder right here. Right? So if we were to be silly about it, it's like a ladder. It's leaning against the wall, which is this, right? And we have rates, basically it's sliding away, which is not good, obviously, but it provides a nice problem for related rates for what we're doing. So basically what we need to do is we need to think about what's going on here. So basically at a given time, the side Y represents how far up the ladder is on the wall, and the side X represents how far from the bottom of the ladder is from the wall. So these are all values that are going to change, and of course the ladder itself is 20 feet according to our given right here that we have. So it says, how fast is the top of the ladder sliding down the wall? Okay. So when they say fast, they mean rate. So if we're talking about the top of the ladder, that means we're referring to this side. So that means that we should be looking for d what dt. So most students by this point are like, oh, that's got to be dy dt. So the rate of change in which the ladder is moving down the wall here must be dy dt. Okay, so that's what we're looking for. Now, what we need then is we need an equation or a formula that will, for this scenario, up here, the ladder, that will allow us to develop a dy dt. Now, another thing that's important is what is given. So it actually gives you two pieces of information about the bottom. It tells you at the exact time that this is 12, it's actually sliding at a rate of 2.5. Well, if this is the length and the slide in which it's rating is dy dt, I said that wrong, but good enough. And that means if this length is 12, the change in which it's moving is dx dt. So if I could create a formula with x and y that also have a dy dt and a dx dt, then I am going to be good as gold to doing this problem. So the question is if I have this scenario, this is clearly a right triangle, what can I do? What formula, famous formula I can apply right now that's going to get me x and y in there? Well, clearly, the Pythagorean theorem. Hopefully, right? So look at this problem. What Pythagorean theorem can we do? X squared plus y squared is equal to 20 squared, which is, of course, going to be just 400. Okay, so this is going to be, believe it or not, our equation for relating the sides to each other in our problem. So what do we need to do? We need to take the derivative with respect to t of both sides of this problem, just like we did in the implicit differentiation section. So ddt of 400. Okay, what do we get? Well, a lot of implicit stuff. So we're going to get 2x dx dt plus 2y dy dt equals 0. Okay, the derivative of a constant is always going to be 0. Okay, next we have our related rates formula. Now we have to look at our given information and plug in what we have. So let's take a look at first x. Okay, so we were given in this problem that 12 feet from the wall. So that is this right here, 12 feet. So that's x. So we can plug in, so we got 2 times 12, right? We were also given the rate of that same side in which it moves. It's 2.5 feet. So this is 2.5. Bring down the 2. Were we given the distance y anywhere? We weren't. We know this is 20, we know this is 12, but we don't know what this is. I claim we can find it. Why? Because the Pythagorean theorem again. We can say that 12 squared plus y squared is equal to 20 squared, and get 144 plus y squared is equal to 400. Y squared is equal to 256, which means the square root of both sides is going to get you plus or minus 16. Clearly, we want just 16. So this is going to give us a side. Now, at this point, what are we trying to find? We're trying to find dy dt, and this is 0. Now, pause button for a second. So, a lot of students, what they'll say to me at this point is they'll say, why didn't we just solve for 16 in the beginning and then just put it into our equation here when we solved this? Or why didn't we use 12 in the beginning when we had this? Because we can find or have both numbers. The problem is that this problem needs rates. You need to have dx dt and you need to have dy dt. The only way to develop a dy and a dx dt is to keep these variables even though we know them as x and y. That's a big part of the strategy of this problem. Okay, so last but not least here, we need to solve. So it looks like it's going to be 60. 2 times 12 times 2.5 is 60, plus 32 dy dt equals 0, which means 32 dy dt is equal to negative 60, which means dy dt is equal to negative 60 divided by 32, which is going to give you approximately negative 1.875, and then we need a label. Okay, so again, if this is how fast the top of the ladder, so this is a singular measure of y, and we need it as a rate. So all we have to do is take it and make it feet per second. Okay, so this is our result. Now there's a little bit of logic here to take a note of. So the answer is negative. So the question is why is it negative, right? Here's why. So this part is sliding in the positive direction away, right? But as this thing is sliding this way, what is this sliding? Down. Which means this is sliding in the decreasing direction, hence why the answer is negative. Okay, so let's try, these are all problems for the same scenario. So what I'm going to do is, again, I'm just going to draw the ladder over here, 20 theta y and x. Okay, it says, how fast is the angle theta changing? Okay, so now we are finding the rate of change of the angle. So that's a whole different can of worms, so to speak. So what do we do with that? Well, if you look at this problem, if we need to find, think about this for a second. If we need to find the rate of change of theta, isn't that d theta dt? Which means we need theta in our problem. Well, what is the only thing that you know of that relates an angle, let's say this, to the sides of a triangle? Hopefully trigonometry is like just blaring in your head right now, because that's exactly what we're going to have to do in order to solve this problem. So what I did was I basically just came up with or utilized variables that were just right in front of me. So for example, I utilized for this problem y and 20, right? So what trig function relates theta to y and 20? So in other words, opposite over hypotenuse. Well, that is clearly going to be sine. So what is the formula? It's the sine theta is equal to y over 20. And I would love to get 20 on the other side, so my formula is going to be 20 sine theta is equal to y. Okay, so instead of an area or a volume formula or Pythagorean theorem, now we're using trig in order to designate what we have. So just like we've done in the past, we need to take ddt of both sides. So I'm going to reverse the sides to make it more comfortable to look at. So ddt of y and ddt of sine theta. Okay, this is our first jump into trig with, this is 20 sine theta. Hold on one second. So this is our first jump into trig. So note 20 is a constant, so we're taking ddt of sine theta here. Okay, so this is our first jump into trig, really, when it comes to related rates. So what does that look like? Well, this clearly is dy dt. 20 stays put. So how do we find the derivative of sine theta? Well, we find the derivative of sine as if theta was t. Well, what's the derivative of sine? It's cosine of theta, but then we have to do the rate of change in the variable, d theta, over time, so d theta dt. So this is going to be our related relates problem that we now have to incorporate into our scenario. So what are we trying to find? We're trying to find how fast the angle is changing. That is this. So our missing variable for our problem is d theta dt. So what is this implying? This is implying that we should know all the other ones. Well, if you look closely, check this out. in letter A, we actually found dy dt. It was negative 1.875. So this we know. 20 comes down for the ride, and then here comes the different scenario for our problem, right? This is the one that's going to be interesting. So the cosine of theta, right? So some students get carried away here. They start like doing things in order to find theta, but in reality, I claim this is easy. Why is it easy? Because we know what the cosine of theta in this problem is. The cosine of theta is adjacent over hypotenuse. And by the way, don't we know what x is? X in our original problem was given as 12, which means the cosine of theta is actually going to be 12 over 20 for our problem. And by the way, just a note, these cancel and you get 12. So all you have to do to find d theta dt is take negative 1.875 and divide by 12. So if you get that, d theta dt is going to be equal to approximately negative 0.1563. All right? So here's the difference, is the label is not something you can really find. Anytime you find the change of an angle with respect to time, it's always the same exact label of radians per whatever time it is, second. So the answer is negative 0.1563 radians per second is the change in how fast that angle is changing as the ladder slides away from the wall. Okay, let's conquer the last part of this problem. It says, how fast is the area of the triangle changing? Okay, so we're back to this triangle, right? That's a great triangle, Jesus. Yx 20, it's a right triangle, right? We're trying to figure out the rate which the area is changing. So hopefully by now, when you see rate of area changing, the first thing you think is, I need a dA dt. So if I need a dA dt, I need an area formula for this triangle. Area, again, is 1/2 base times height, but the base is here and the height is here, so it's going to be area equals 1/2 xy. So with what we're doing here, we can basically we can come up with our formula by taking the derivative of both sides of this with respect to t. Oh, actually, here we have a constant of 1/2, so let's bring that in at the beginning here. And multiply by, or take the derivative of xy. So, yeah, I said multiply only because if you look at this right here, we have the derivative of a product, which means we're going to need the product rule, which means we'll have dA dt is equal to 1/2. Then remember it's f prime g plus fg prime, so we have to take, just be careful, this is ddt of x times y plus x times ddt of y. And then if we rewrite that, keep the half, I guess, we're going to get, let's put this in order, so y times dx dt plus x times dy dt. Alright, so over the scope of this entire problem, there are 4 variables over on the right side of this equation right here, right? But we have all of them. We have x, which was 12. We have y, which we calculated to be 16. 16 here. Y was 12. We have dx dt, which was given as 2.5. And we computed dy dt to be negative 1.875. So all we're going to do is we're going to plug all of those numbers into our equation. So we're going to get dA dt, which is what we're trying to find, is equal to 1/2. We have our y, which is going to be our 16. We have 2.5, which is our rate of change of x. Let me get rid of this. We have plus, don't love that. Drew with the eraser even though I didn't intend to. We got 12 for our x and negative 1.875 for our value of our change in y. So if we do the calculations we're going to get 8.75. And then because it's area and we have feet in second, it's feet squared per second, which means this is our answer. So as the ladder moves away from the wall, the area is actually increasing at a rate of 8.75 feet squared per second. Okay, we end with most assuredly the most challenging problem in this section, and really the hardest one you'll actually find. So I won't give you anything more difficult than this. It says a water tank is in the shape of a right circular cone, so you see that over to the right, and has a height of 20 feet. So you see that's labeled on the diagram. The top rim of the tank is a circle with a radius of 10 feet. That's also labeled. The water is being pumped into the tank at a rate of 2 cubic feet per minute. So right away, hopefully your sensors go, oop, that's volume, cubic feet per minute. What is the rate of the change of the water depth in feet per minute when the depth is 12 feet? Okay, so a lot of things should be going through your head here, hopefully in the beginning here. For example, this has to be dV/dt, first of all, cubic feet per minute, rate in which it's changing. They're asking for the rate of change of water depth. Well, the depth in this problem of the water is designated by the variable h. So the rate of change of that's got to be dH/dt. And they're also saying the depth of the water is 12, which means that's h. Okay, so we're going to need a formula that relates the volume of a cone to its height. We also have radius going on in our problem, which will come in into a second. But in the beginning here, we at least need the volume formula for a right circular cone. So what is that? It's volume equals 1/3 pi r squared h. Okay, so one of the issues between this, so when we did all the other area and volume problems, right? It was always volume and then one variable on the other side. It was volume and one variable on the other side. And volume and, again, one variable. You see where we're going with this? So if we go, or area and one variable on the other side. If we go to our problem here, we have two variables on the other side. Okay? While that's okay in some scenarios, it's not going to be in this one. So in these circular cone problems, or cylinders are another option, what we do is we need to convert r or h into the other variable somehow. Now it turns out that we're given h in this problem over here, right? Because we're given h, we would ideally, and dH/dt, we would ideally want to turn r into something involved with h. So that's the first scope of our problem. How can we do that? So when you look at this picture, it is important to see that there is a lot going on. So for example, if you look at this right here, okay, this is h, right? We actually have a perfect right triangle right here. And if you actually look above it, let's say we did this, went this way, we actually have another, this is 20, the whole thing, we have another right triangle. But if you recall, you might not, but if you recall from geometry, we can do the right triangle on the other side, right? And we can get 20 for the whole thing. Because they are both right triangles and they share this angle, they are called similar triangles, which means that their sides are going to be in proportion. So what does that mean? That means that if we take the radius of the small circle, or this down here, so the radius of the small circle, to the height of the cone, the radius of the cone to the height of the cone, that is going to be the equivalent of the radius of the big cone to the height of that cone. So what's the radius of the big cone? 10, and the height of the big cone is 20. So let me do this again. I'm going to erase everything. So basically we have 10 to 20 is the ratio of the big cone to radius to the big cone's height, right? But then we also have another cone shape created by the water down here, where we have a height and a radius. So this proportion is legal. And what we can do with that proportion is we can multiply both sides by h and get r is equal to, we can 10/20 h, which means r is equal to 1/2 h. Okay, so look what happens. We can now take this ratio and put it right here. And by doing so, we're going to consolidate into one variable. So let me do a little bit of algebra here. So this is going to end up being, it looks like, did I not put the h in? Jesus. Okay, h has to go in there, obviously. So what does that look like? Well, this right here is 1/4 h squared, right? So what are we going to get? We're going to end up with volume is equal to 1/3 pi times 1/4 h cubed for our problem, and then the fractions can multiply to get 1/12 pi h cubed as our variable for the scope of our problem. So this is actually the volume of this cone, 1/12 pi h cubed. And we did so by using this nice similar triangle proportion formula and then changing it into one variable. Okay, once we have this, we can then go ahead and do our derivative work. So d dt of v equals, we're going to take our 1/12 pi, which is a constant, move it over, and we're taking d dt of h cubed. So what does that look like? Excuse me. So dv dt is equal to 1/12 pi. We're going to get 3h squared times dh dt. If we simplify this, we're going to get dv dt is equal to this. So actually, let's do, So 12 and 3 actually simplify and get 1/4. And then we're going to get pi and then h squared dh dt. Okay, so this is essentially our related rates formula. So what do we need to do? We now need to look at our problem and substitute in the proper variables. So what did they say? Well, the first given was that the water tank has a height of 20 feet. We don't care about the height of the tank anymore. We only care about what's going on with the water. Okay, that's the key concept right now. All of this is the water. So the top of the tank of the circle is 10 feet. Again, that is the top of the tank. So anything after that is important. It says if the water is being pumped into the tank at a rate of 2 cubic feet per minute, so that is here, 2. So 1/4 pi continues. What is the rate of change of water depth? What is dh dt when the depth is right here, 12 feet? So 12 squared times dh dt, which is our missing information. So all we have to do is the math here. It looks like this is going to be 1/4 of 144, which is 36 pi. So in the next step, we're going to get dh dt is equal to 2 over 36 pi. So the result, basically, if I leave some room for some labels here, I'm going to get feet per minute, because we're doing a single measure of the height of the cone and how it changes. So that is going to be your result. Note that is approximately 0.0177 in case you're doing that, let's say, in my math lab and they want a decimal answer. This problem is, a big one. It has a lot involved with it. You'll see that a lot of these sections will get quite complicated and diverse in the type of problems that you follow, but you have to be able to conquer any related rates problem up to this skill level.